Overloading is like giving a single name many different jobs depending on the situation. A function is a little robot that does a task. Overloading lets you have several robots with the same name but different tools. For example, a function called print can print a string, a number, or a picture. Operator overloading does the same thing for symbols such as plus or asterisk. Instead of always adding numbers, the plus symbol can also join two strings, combine two vectors, or merge two sets. The core idea is polymorphism, one name many forms, and the compiler decides which form matches the given arguments. Think of a Swiss Army knife. The blade, screwdriver, and scissors all share the same handle, the name, but you pull out a different tool, the implementation, depending on what you need. In a programming language, you write each version with a slightly different signature, the list of parameter types. The compiler builds a catalog of all the versions, the overload set, and later when you call print 42, it looks in the catalog for the version that matches a single integer argument. Different languages have their own spelling rules for overloading. In C++, you write several functions with the same name but different parameter lists. Int add int a int b semicolon adds two integers. Double add double a double b semicolon adds two doubles. Std string add std string a std string b semicolon concatenates strings. The declaration rules say that the name must be identical, the parameter types must differ, and the return type alone cannot create a new overload. You cannot overload just by changing what is returned. When the source code is compiled, the compiler performs name mangling. It rewrites each overloaded name into a unique internal name that includes the types like add underscore int or add underscore double. This lets the linker treat them as separate functions, while the programmer sees only one friendly name. The resolution mechanism works in two steps. Step 1, lookup, find all functions with the requested name in the current scope. Step 2, viability test, discard any that cannot be called with the given arguments, wrong number, impossible conversion. The remaining candidates form the overload set that will be examined in the next topic. When the compiler has a list of possible overloads, it tries to pick the best one. It does this by comparing how close each candidate's parameters are to the arguments you gave. Exact match, the argument type is exactly the same as the parameter type. This is like fitting a puzzle piece that is the right shape. Example, calling add 510 matches int add int perfectly. Promotion, the compiler can promote a smaller type to a larger compatible type without losing information. Think of putting a small Lego block into a bigger hole, it still fits. Example, a char can be promoted to an int, so add a 3 may match int add int after promotion. Conversion, if promotion is not enough, the compiler looks for user-defined or built-in conversions like constructing a std string from a C-style string. This is the least preferred because it may involve extra work, like turning a raw number into a complex object. The compiler builds a hierarchy, exact greater than promotion greater than conversion. It picks the first overload that wins in this hierarchy. If two overloads are equally good, the call is ambiguous and the compiler will give an error. Good overload design is like making a toolbox that is easy to understand for anyone who uses it. Consistency, all overloads should behave in a similar way. If plus adds numbers, it should also combine objects in a natural way, for example vectors. Mixing plus to sometimes concatenate strings and sometimes subtract values would confuse users. Predictability, the compiler should always choose the same overload for the same call. Avoid writing two overloads that are only different by a tiny conversion, because the compiler might flip between them depending on subtle changes. Minimal surprises. Do not overload operators in ways that break common expectations. For example, overloading operator exclamation, logical not, to delete a file would surprise a programmer who thinks not X simply means not true. Child-friendly analogy. Imagine a vending machine that has a button labeled snack. If pressing the button sometimes gives chips, sometimes a candy bar, and sometimes a drink, the user gets confused. Keep each button's result consistent so the user knows exactly what to expect. Inlining, modern compilers often replace a small function call with the actual code inline to avoid the overhead of jumping to another place. When many overloads exist, the compiler may not inline all of them, especially if the overload set is large, which can keep some function call cost. Code bloat, each overload generates its own machine code. If you overload a function for every combination of int, float, double, long, etc., you may end up with many similar copies of code, making the executable larger. This is like printing many copies of the same recipe with tiny ingredient changes. It wastes paper. Runtime overhead. The selection of the right overload happens at compile time, so there is no extra cost when the program runs. The only runtime cost is the normal function call overhead. However, if you rely on user-defined conversions, those conversions themselves may add work, for example, constructing a temporary object. To keep performance healthy, overload only when it adds clear value. Keep overload set small and let the compiler inline the most used versions. Explanation: a classic math example is a vector dash, a list of numbers that represents a point in space. By overloading the arithmetic operators, we can write code that looks exactly like the math we learn in school. Struct vec2 with double x and y addition operator plus takes a const reference to a vec2 and returns a vec2 with x plus rhs.x, and y plus rhs.y subtraction operator minus returns a vec2 with x minus rhs.x, and y minus rhs.y scalar multiplication operator times takes a double s and returns a vec2 with x times s, and y times s then vector a with values 1.0 and 2.0. Vector b with 3.0 and 4.0, c equals a plus b, d equals a times 2.5. X sub 1, y sub 1 plus x sub 2, y sub 2 equals x sub 1 plus x sub 2, y sub 1 plus y sub 2. The overloaded operator plus implements exactly this rule, letting programmers write a plus b instead of calling a function like add vec open parenthesis, a comma b close parenthesis. The same idea works for matrices. Overloading star can perform matrix multiplication, which follows the formula. C sub ij equals sum over k of a sub ik times b sub kj. Matrix operator times takes a const reference to a left-hand side matrix and a const reference to a right-hand side matrix and computes the product. Matrix result equals a times b, which looks just like the math equation. These overloads make scientific code easier to read, reduce mistakes, and match the way we talk about math on a chalkboard. Explanation: even though overloads are powerful, they can cause hidden problems. Ambiguity: if two overloads are equally good, the compiler cannot decide which one to use. Example: void f int, void f double, f5 comment. Int 5 can match both int exact and double promotion. Usually the int version wins, but adding another overload like f long may make it ambiguous. Hidden conversions: a user-defined conversion constructor can turn one type into another behind the scenes. This can make a call select an overload you didn't expect. Struct string with conversion constructor from const char pointer. Void print string, void print int, print hello, comment. Calls print string because of the conversion, not print int. Unintended symmetry. Operators are often expected to be commutative. Order doesn't matter for addition, but if you overload only one side, the other direction may fail. Vec2 operator plus with left-hand side vec2 reference and double s. Comment, vec2 plus scalar works. Comment, scalar plus vec2 is missing, compiler error. To avoid these traps, keep overload sets small, limit implicit conversions, and provide both directions for symmetric operators. Explanation: many real-world libraries use overloads to give programmers a smooth experience. Standard library C++, std: ostream: operator less is overloaded for int, double, std: string, and many custom types. This lets you write std: count less 42 less apple, and the compiler picks the right overload for each argument. STL containers. std: vector: pushback is overloaded in some frameworks to accept both const t reference and t r-value reference move semantics. The overload that matches the value category of the argument is chosen, giving optimal performance without the user having to think about it. Graphics frameworks. In a game engine, the plus operator may be overloaded for a color class to add two colors, while star operator may be overloaded to blend a color with a scalar opacity. The overload set mirrors how artists think about mixing paints. Domain-specific languages. In linear algebra libraries like eigen, many operators plus, minus, star, slash are overloaded for matrices, vectors, and scalar combinations. The library uses expression templates to keep performance high while presenting a natural mathematical syntax. These examples show how overloading, when used carefully, can turn a collection of low-level functions into a friendly expressive API that feels like speaking the language of the problem domain.